August 17, 2017. At precisely 8:41 a.m. Eastern Time, a ripple passed through Earth. It was invisible, intangible, yet it stretched and squeezed every atom on our planet, including every atom in your body, by a distance smaller than the width of an atomic nucleus. This cosmic whisper had traveled for 130 million years across the void of space, carrying news of a cataclysmic event that had occurred when dinosaurs still ruled this planet. Two dead stars, each compressed to the density of an atomic nucleus, each spinning hundreds of times per second, had been locked in a death spiral. For perhaps 1 billion years, they orbited each other, drawing closer with every passing century. And finally, moving at 1/3 the speed of light, they collided. The impact lasted less than a second. In that eye blink, the universe performed the most extraordinary act of alchemy ever witnessed. It created gold, platinum, uranium, every heavy element in the periodic table, forged in temperatures exceeding 1 trillion degrees, in conditions so extreme they make the core of our sun look like a gentle candle flame. The explosion released more energy in 1 second than our sun will produce in its entire 10 billion year lifetime. It was 1,000 times brighter than a supernova, bright enough to be seen across half the observable universe. Scientists call this event a kilonova, and on that August morning in 2017, for the first time in human history, we didn't just see it happen, we felt it. We heard the dying scream of colliding neutron stars rippling through the fabric of spacetime itself. The gold ring on your finger was born in such an explosion, long before Earth existed. Every precious metal, every rare element heavier than iron in your body, in your technology, in our planet, all of it came from events like this one. This is the story of how we discovered cosmic alchemy, how we learned that the universe creates gold through the most violent collisions imaginable, and how August 17, 2017 changed astronomy forever. Chapter 1: The Alchemist's Dream. For thousands of years, humans dreamed of turning common metals into gold. Medieval alchemists devoted their lives to this quest, heating and mixing substances, searching for the philosopher's stone, a legendary material that could transmute base metals into precious ones. They failed, not because they lacked skill or dedication, but because they were trying to do something that requires the most extreme conditions in the universe. You cannot create gold in a laboratory. You cannot make it through chemistry. Gold isn't created, it's forged in the heart of cosmic violence. To understand why, we need to understand where elements come from. The Big Bang, 13.8 billion years ago, created only the 3 lightest elements: hydrogen, helium, and traces of lithium. That's it. For hundreds of millions of years, the universe was nothing but clouds of these primordial gases. Then the first stars ignited. In their cores, temperatures reached 15 million degrees Celsius. At these temperatures, hydrogen nuclei slam together with enough force to overcome their electrical repulsion and fuse into helium. This nuclear fusion releases enormous energy. It's what makes stars shine. As stars age, they create heavier elements through successive fusion reactions. Helium fuses into carbon, carbon into oxygen, oxygen into silicon. Each step requires higher temperatures and pressures. Massive stars, those 8 times more massive than our sun, continue this process until they produce iron. And then they stop. Iron is the most tightly bound nucleus in nature. Fusing iron requires energy instead of releasing it. An iron core cannot sustain a star through fusion. The core becomes a ticking time bomb. When a massive star develops an iron core about 1.5 times the mass of our sun, catastrophe strikes. The core collapses in less than a second. Electrons are crushed into protons, creating neutrons. The outer layers of the star fall inward at a quarter of the speed of light, rebound off the ultradense core, and explode outward in a supernova. This supernova can create elements heavier than iron through rapid neutron capture. But there's a problem. Supernovae don't produce enough heavy elements to match what we observe in the universe. Astronomers calculated that if supernovae were the only source, our galaxy should have far less gold, platinum, and uranium than it actually contains. There had to be another source, something even more violent than a supernova, something that could create heavy elements in quantities that match cosmic abundances. That something is a kilonova. Chapter 2: Neutron Stars, the Densest Matter. To understand kilonovae, we must first understand their ingredients: neutron stars. When a massive star explodes as a supernova, if the core's mass is between about 1.4 and 3 solar masses, it doesn't form a black hole. Instead, it creates something almost as bizarre: a neutron star. Imagine taking the entire mass of our Sun, 330,000 times the mass of Earth, and compressing it into a sphere just 20 kilometers across. That's roughly the size of Manhattan. The density is incomprehensible. A teaspoon of neutron star matter would weigh 1 billion tons on Earth, more than the entire human population weighs combined. This isn't ordinary matter. The intense gravity has crushed atoms out of existence. Electrons have been forced into protons, converting them into neutrons. The star is essentially one giant atomic nucleus, held together not by electromagnetic forces, but by the sheer weight of its own gravity. Neutron stars spin fast. Some rotate hundreds of times per second. Imagine something with the mass of our Sun spinning faster than a kitchen blender. Their magnetic fields are the strongest in the universe, 1 trillion times stronger than Earth's. They warp spacetime around themselves, creating distortions in reality itself. And sometimes, neutron stars come in pairs. When a binary star system contains 2 massive stars and both explode as supernovae, they can leave behind 2 neutron stars orbiting each other. These binary neutron stars are cosmic time bombs. As they orbit, they emit gravitational waves, ripples in spacetime predicted by Einstein's general relativity. These waves carry away energy, causing the orbit to shrink, slowly at first. The 2 neutron stars might orbit for billions of years, separated by thousands of kilometers. But gravitational wave emission increases dramatically as the stars get closer. The orbit tightens faster and faster. Years shrink to months, then days, then hours. In the final moments, the neutron stars are orbiting each other hundreds of times per second, just a few hundred kilometers apart, moving at a significant fraction of light speed. And then they collide. Chapter 3: The Collision. When 2 neutron stars merge, they create conditions that have no parallel anywhere else in the universe. The collision doesn't happen all at once. As the stars spiral inward during those final milliseconds, tidal forces begin to deform them. Neutron stars, despite being the densest objects this side of a black hole, aren't perfectly rigid. The immense gravitational pull from each star stretches the other, creating tidal bulges. Matter begins to tear away from the surfaces. Superheated material, compressed beyond anything achievable in laboratories, starts streaming into space. This material is almost pure neutrons, billions upon billions of free neutrons flying through space at tremendous speeds. Then comes the impact. 2 city-sized objects, each weighing more than our Sun, collide at 1/3 the speed of light. The energy released in that instant is staggering, more than all the light emitted by every star in the Milky Way combined. Temperatures spike to over 1 trillion degrees, 70 times hotter than the center of the Sun. The collision creates a shockwave that ripples outward at relativistic speeds. More material is ejected. Perhaps 5,000 times the mass of Earth worth of neutron-rich matter blasts into space in all directions. What happens next depends on the combined mass. If the merged object is below about 2.5 solar masses, it might form a massive neutron star, a hypermassive neutron star spinning at over 1,000 times per second. This object is unstable but might survive for seconds, minutes, or even longer before collapsing. If the mass is greater, the object immediately collapses into a black hole, surrounded by a swirling disk of superheated debris. But regardless of the final outcome, those thousands of Earth masses of neutron-rich material are now flying through space. And in those expanding clouds, cosmic alchemy begins. Chapter 4: Forging Gold. The key to creating gold and other heavy elements is neutrons. Lots of them. Free neutrons that can be captured by atomic nuclei. In ordinary matter, neutrons are locked inside atomic nuclei bound to protons. But in the aftermath of a neutron star collision, trillions upon trillions of neutrons are flying free, liberated from the gravitational prison of the collapsed stars. These free neutrons encounter atoms in the expanding debris, mostly iron and lighter elements. When a neutron collides with an atomic nucleus, it can stick, increasing the nucleus's mass. This process is called neutron capture. In most cosmic environments, neutron capture happens slowly. A nucleus might absorb a neutron, then wait thousands or millions of years before capturing another. This slow process, S-process, occurs inside aging giant stars and produces many elements, but it cannot create the heaviest ones. But in a kilonova, neutron capture is rapid, so rapid that scientists call it the R process, rapid neutron capture. Nuclei are bombarded with neutrons, capturing them faster than they can decay. A single nucleus might capture dozens of neutrons in less than a second. This creates highly unstable, neutron-rich isotopes that don't exist naturally anywhere else. These isotopes then decay through beta decay. A neutron converts into a proton, emitting an electron and a neutrino. This increases the atomic number, transforming one element into another. Iron absorbs neutrons and becomes unstable iron isotopes, which decay into cobalt, then nickel, then copper, then zinc. The process continues up the periodic table. Capture enough neutrons, allow enough decay cycles, and you get gold, platinum, uranium, all the elements heavier than iron, all the way to the edge of stability. The R process can produce elements all the way up to californium and beyond. Elements so heavy and unstable they don't even have stable isotopes. These elements immediately begin decaying, releasing energy. And that energy makes the kilonova glow. Chapter 5: The Light Show. Unlike neutron stars themselves, which emit virtually no visible light, a kilonova is a spectacular light show that lasts for days or weeks. The mechanism is radioactive decay. Those freshly created heavy elements are unstable. They decay into lighter, more stable isotopes, releasing energy in the form of heat and electromagnetic radiation. This is similar to how supernovae glow, but with crucial differences. A kilonova's light changes color over time in a characteristic way. In the first hours and days, it glows blue and bright. Wavelengths of light are emitted by relatively lighter elements created in the collision's outer layers. As time passes, the expanding debris cools and the light shifts to red and infrared, the signature of the heaviest elements, including lanthanides, rare earth elements, and actinides like uranium. The name kilonova reflects its power. A typical nova, a thermonuclear explosion on a white dwarf surface, has a luminosity of about 100,000 suns. A supernova is roughly 100 times brighter, at about 10 million suns. A kilonova sits right between them, about 1,000 times brighter than a nova, hence kilonova, kilo meaning thousand. But unlike supernovae, which can shine brightly for months, kilonovae fade quickly. Within a week, the optical light has faded to near invisibility. Within a month, even infrared telescopes struggle to detect them. This rapid fade happens because the expanding debris quickly becomes transparent. The material spreads out, density drops, and photons can escape more easily. The light we see isn't coming from a glowing surface, but from throughout the volume of expanding gas. The exact color and brightness depend on what elements are present. Lighter elements, strontium, zirconium, produce blue light. Heavier lanthanides, lanthanum, cerium, neodymium, create red light because they absorb blue wavelengths. The very heaviest elements, gold, platinum, uranium, glow in the infrared. By analyzing the spectrum of light, the specific wavelengths present, astronomers can identify which elements were created. This spectroscopy is like cosmic fingerprinting. Each element absorbs and emits light at characteristic wavelengths, leaving a unique signature. And on August 17, 2017, for the first time, humanity captured that signature in detail. Chapter 6, GW170817, The Discovery. The detection began with a whisper, a gravitational wave so faint it stretched space by less than 1/10,000th the diameter of a proton. The LIGO detectors in Louisiana and Washington state registered it simultaneously. These L-shaped instruments, with arms 4 kilometers long, use laser interferometry to measure the tiny stretching and squeezing of space caused by passing gravitational waves. Advanced LIGO is sensitive enough to detect distance changes smaller than a proton's diameter across those 4-kilometer arms. At 8:41:04 a.m. Eastern Time, both detectors saw the same signal, a chirp that lasted about 100 seconds, rising in frequency from 30 Hz to over 1,000 Hz. This long duration immediately identified it as something different from previous gravitational wave detections, which had all been black hole mergers lasting less than a second. This was a neutron star collision. The Virgo detector in Italy, which had just joined the observation run weeks earlier, also recorded the event, though more weakly. This 3-detector observation allowed precise triangulation of the source's location in the sky to a region of just 28 square degrees, small enough that optical telescopes could search it. Just 1.7 seconds after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope detected a short burst of gamma rays coming from the same region of sky. This was the smoking gun, direct confirmation that neutron star mergers produce short gamma ray bursts, something astronomers had theorized for decades but never proven. Within minutes, an alert went out to observatories worldwide. Gravitational waves have been detected, and there's an electromagnetic counterpart. Find it. The race was on. Chapter 7, The Global Hunt. 12 hours after the gravitational wave detection, 3 independent groups of astronomers found it. Using the 1-meter swope telescope at Las Campanas Observatory in Chile, a team spotted a new point of light in galaxy NGC 4993, located in the constellation Hydra about 130 million light-years from Earth. This was humanity's first optical observation of a kilonova, the afterglow of colliding neutron stars. Within hours, more than 70 observatories around the world and 7 space-based telescopes were pointed at this single spot. It was the most extensive, coordinated observation campaign in astronomical history. The Hubble Space Telescope captured detailed images and spectra over the following weeks. The Chandra X-ray Observatory searched for high-energy emission. The Very Large Array radio telescopes in New Mexico monitored long-wavelength radiation. Infrared telescopes tracked the fading afterglow. What they saw matched theoretical predictions with stunning accuracy. In the first few days, the optical light was bright and blue, with a nearly featureless spectrum. Exactly what models predicted for the outer layers of expanding debris containing lighter R-process elements. As days passed, the light faded and reddened. By 1 week post-merger, the optical light had dropped to just 10% of its peak brightness. But infrared observations revealed something spectacular. Broad features in the spectrum indicating rapid expansion, about 10% of light speed, and the presence of very heavy elements. The infrared glow persisted for weeks, powered by the radioactive decay of freshly synthesized gold, platinum, and heavier elements. Spectroscopic analysis identified specific elements: strontium, lanthanum, cerium, and others. Computer simulations comparing theoretical spectra with observations confirmed that the Kilonova had created massive quantities of R-process elements, elements that can only form through rapid neutron capture. Researchers calculated that this single event produced about 16,000 Earth masses of heavy elements. Of this, approximately 10 Earth masses were pure gold and platinum. 10 Earths worth of gold and platinum created in less than a second. Chapter 8: Gravitational Waves, Ripples in Spacetime. The gravitational wave detection itself was a triumph decades in the making. Albert Einstein predicted gravitational waves in 1916 as a consequence of general relativity. According to his theory, massive objects accelerating through space create ripples in the fabric of spacetime that propagate outward at the speed of light, like ripples on a pond. But Einstein was skeptical they could ever be detected. The effect is incredibly tiny. Even the most violent cosmic events, like colliding neutron stars, produce gravitational waves that stretch space by less than 1 part in 1021 by the time they reach Earth. For decades, gravitational waves remained theoretical. Then in 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, 2 neutron stars orbiting each other, and measured its orbit with incredible precision over years. They found the orbit was shrinking at exactly the rate general relativity predicted if the system was losing energy to gravitational waves. This indirect evidence won them the Nobel Prize in 1993. But direct detection required extraordinary technology. LIGO, Laser Interferometer Gravitational Wave Observatory, took over 40 years and hundreds of millions of dollars to build. Each detector consists of 2 4-kilometer-long arms at right angles. A laser beam is split, travels down each arm, reflects off mirrors, and recombines. When a gravitational wave passes through, it stretches one arm while compressing the other, creating an interference pattern in the recombined laser light. The sensitivity required is mind-boggling. To detect neutron star mergers across 100 million light-years, LIGO must measure length changes of 10 meters, about 1/10,000th the diameter of a proton. It's like measuring the distance to the nearest star to within the width of a human hair. LIGO began operations in 2002 but didn't detect anything for years. In 2010, it shut down for a major upgrade. Advanced LIGO came online in September 2015. On September 14, 2015, just days after turning on, Advanced LIGO detected its first gravitational waves from two merging black holes 1.3 billion light-years away. This discovery, announced in February 2016, won the Nobel Prize in Physics in 2017. But GW170817, the neutron star merger detected in August 2017, was different. Unlike black holes, which emit no light, neutron star mergers produce spectacular electromagnetic fireworks. This was multi-messenger astronomy, observing the same event through both gravitational waves and light. The combined observations proved several things. Gravitational waves travel at the speed of light to within 1 part in 10, ruling out many alternative theories of gravity. The time delay between the gravitational wave and the gamma-ray burst told us about the physics of the merger. The optical and infrared light confirmed heavy element production. X-rays and radio waves detected later revealed details about jets of material. GW170817 was astronomy's Rosetta Stone, one event that confirmed multiple theories and opened new ways to study the universe. Chapter 9: Rewriting the Periodic Table. The observations of GW170817 definitively answered a question that had puzzled astronomers for decades. Where do the heaviest elements come from? For years, scientists had theoretical models suggesting neutron star mergers could produce heavy elements through the ARP process. But models are just predictions. Until GW170817, there was no direct observational proof. The Kilonova's spectrum provided that proof. The infrared emission, the color evolution, the spectroscopic features, everything matched the signature of freshly synthesized heavy elements decaying and releasing energy. Researchers could even estimate quantities. Based on the total luminosity and the rate at which the light faded, they calculated that GW170817 produced about 16,000 Earth masses of total ejecta, approximately 10 Earth masses of gold and platinum combined, significant amounts of uranium, though exact quantities are harder to measure, the full range of lanthanides and other heavy elements. To put this in perspective, all the gold ever mined by humans throughout history totals about 200,000 metric tons. The GW170817 Kilonova produced roughly 3 times 10^25 kilograms of gold. That's 3 followed by 25 zeros, or about 150 trillion metric tons. More gold than exists in thousands of Earths. And this was just 1 kilonova. These events happen regularly across the universe, perhaps once every 10,000 to 100,000 years per galaxy. Over cosmic time, countless kilonovae have enriched the universe with heavy elements. Astronomers estimate that merging neutron stars are responsible for roughly half of all elements heavier than iron in the universe. The other half comes from other sources like supernovae and collisions between neutron stars and black holes. But for the very heaviest elements, gold, platinum, uranium, thorium, kilonovae are the dominant source. Every gold atom in your jewelry, every platinum atom in catalytic converters, every uranium atom in nuclear reactors. They were all forged in the heart of a kilonova billions of years ago, expelled into space, mixed into clouds of gas and dust, and eventually incorporated into the material that formed our solar system. You wear the remnants of cosmic violence around your finger. Chapter 10: The Future of Kilonova Science. GW170817 was just the beginning. As gravitational wave detectors become more sensitive and additional observatories come online, we'll detect many more neutron star mergers. LIGO and Virgo are currently in their fourth observing run with improved sensitivity. A third detector, KAGRA in Japan, came online in 2020. A fourth, LIGO India, is under construction. With more detectors spread across the globe, we'll localize gravitational wave sources more precisely and detect fainter signals from greater distances. Future detectors will be even more powerful. The Einstein telescope, proposed for construction in Europe, would have 10-kilometer-long arms and operate underground for better vibration isolation. It could detect neutron star mergers throughout the entire observable universe. The space-based LISA, Laser Interferometer Space Antenna, will launch in the 2030s to detect lower-frequency gravitational waves from merging supermassive black holes and other sources. Though LISA won't see neutron star mergers, they're too high frequency, it will revolutionize gravitational wave astronomy. On the electromagnetic side, new surveys like the Vera C. Rubin Observatory will scan the entire sky every few nights, catching kilonovae as they brighten and fade. The James Webb Space Telescope, with its exquisite infrared sensitivity, can capture detailed spectra of kilonova emission, identifying specific isotopes created in the explosion. Each new kilonova observation teaches us something about nuclear physics, how matter behaves at densities beyond anything achievable in laboratories, about general relativity, whether Einstein's equations hold in the most extreme gravitational fields, about the equation of state of neutron stars, the relationship between pressure and density in ultradense matter, and about cosmology, because gravitational waves give us a direct measure of distance to the source based on the wave's amplitude, and electromagnetic observations tell us the source's redshift, how fast it's moving away. Each kilonova is a standard siren, analogous to standard candles used in traditional distance measurements. With enough kilonovae observations, we can measure the expansion rate of the universe independently of other methods. This could help resolve the Hubble tension, the troubling discrepancy between different measurements of how fast the universe is expanding. Epilogue: Cosmic alchemy continues. Right now, somewhere in the universe, two neutron stars are spiraling together. Perhaps they're just a few thousand orbits from collision. Perhaps they'll merge tomorrow, or next year, or 1,000,000 years from now. When they collide, they'll create another kilonova. More gravitational waves will ripple through space-time. More gamma rays will flash into space. And more heavy elements, gold, platinum, uranium, will be forged in temperatures exceeding 1,000,000,000,000 degrees. The material will spread into the surrounding space, mixing with interstellar gas. Over millions of years, it will be incorporated into new molecular clouds. Those clouds will collapse under gravity, forming new stars and planets. And someday, billions of years from now, intelligent beings might evolve on one of those planets and wonder where the gold in their world came from. The cycle continues. Death and creation, destruction and synthesis. The universe transforms simple hydrogen into complex elements through the most violent processes imaginable, then scatters those elements across the cosmos to seed the next generation of worlds. We are made of stardust, not just the common elements like carbon and oxygen forged in the cores of ordinary stars, but the rare and precious elements created in cosmic catastrophes. The iron in your blood came from dying stars. The gold in your jewelry came from colliding neutron stars. You carry within you the legacy of ancient violence, transmuted over eons into the matter of life. Medieval alchemists dreamed of turning lead into gold. They failed because they were thinking too small. The universe doesn't turn lead into gold, it creates gold from scratch, in explosions so powerful they shake the fabric of reality, in temperatures hotter than any star's core, through processes that require the density of atomic nuclei and the fury of cosmic collision. We've watched it happen. On August 17, 2017, we felt the gravitational waves and saw the light. We measured the spectrum and identified the elements. We confirmed beyond any doubt that Kilonovae are the universe's gold factories. The ancient dream of alchemy is real, but it takes colliding neutron stars to make it happen. The universe is the ultimate alchemist. And now, finally, we understand its recipe.